Okay, let's ask the question, what does general relativity tell us about the universe as a whole? So let's try to apply these ideas to the entire universe, and let's adopt the following premises. Space, let's see, observationally, space is mostly empty. Basically, what we want to say is that there's very little curvature to space-time. And on very large scales, it's also basically the same everywhere. So this is looks like a good assumption. It's an approximation. Space is the same on large scales, right? This is an approximation. So it also allows us to solve the equations in a straightforward way. Let's say the invariant interval is still an invariant, or it is not time dependent. Right, so the ds squared equals blah, blah, blah. This quantity is, as we thought of it before, it's just some fixed quantity. But no time dependence in this quantity, but we want space-time not to be static, right? This is unlike the Schwarzschild solution. Space-time is not static, so it sort of means that what we need is something like, right, we have a dt squared plus, let's just use coordinates dx, dy, and dz, Cartesian coordinates. If we think of space as Euclidean, space-time is not static, so we could put coefficients in front of here that are time-dependent. But if we do both of these, that would make this whole thing time-dependent, and it would be a little strange here to say that at some location, the rate at which clocks run varies. So all of this together sort of allows us to consider some coefficient there, and here we'll have the usual minus c squared dt squared, where the function is just 1 here. So the equations that we want to solve, of course, are still right, the Einstein equation still looks like that. Our constant we got from the Newtonian correspondence looks like that. Of course, we have the Riemann tensor. This looks like, right, it's going to be derivatives of the connection coefficient, which are functions of this. So let's remind ourselves we need to figure out what these terms are, minus CCD, gamma D AB, and here we have a minus sign, gamma C BD, gamma D CA, with gamma ACB being the 1/2, the inverse metric AD, the derivative of G, DB, and XC, derivative GDC in XB minus derivative GCB in XD. Right? Unlike Schwarzschild, this part is not zero. And so maybe the simplest assumption is to take density of matter multiplied by 4 velocities, UA, UB. It's really the upper TAB upper that is well motivated in terms of 4 velocities, but that's the lowered version. Of course, this is going to basically tell us that h of t depends, well, let's say connected to the density of matter. Right, this is our theory about what is in, what's doing the curving of space-time. And so that's going to, this quantity here will appear, and here will be related to rho in this way. We might want to recognize that we have, this is this diagonal quantity, TATA, that is GAB, TAB. We've seen something like this before. Given the metric that we have, or no off diagonal terms, plus G11, T11, G22, T22, and G33, T33. Let's make life even easier for us by saying that this stuff is actually at rest. All right, so only U0 survives. So we basically are U1 equals U2 equals U3 equals 0. And of course, this will translate into the lowered components. And so this becomes G naught naught, T naught naught, which brings in a minus sign there. This ends up looking like minus density times C squared. And so ultimately the equation that we're going to be solving, let's write this out on another sheet. The equation that we care about to understand about the universe as a whole looks like RAB. We know how to do this from Schwarzschild, and we're going to set this equal to the constant K times TAB plus rho C squared over 2 GAB. And this whole thing will produce some constraint on the quantity that's in our metric, and we'll see what this looks like. So that's our project.